Hi students. So today we are going to discuss the pulse field gel electrophoresis. The pulse field gel electrophoresis technique was conceived by Schwartz and Cantor in 1948 to allow the electrophoretic separation of DNA molecules several megabases in size. This was necessary for the development of megabases mapping and cloning techniques because all linear double-stranded DNA molecule larger than a certain size migrate through the agarose gel at the same time. Agarose gel electrophoresis is a standard technique for separating nucleic acids. Large DNA fragments are unable to migrate through the gel matrix by the same sieving mechanism that small fragments do. Ordinary agarose gel electrophoresis fails to separate extremely long DNA molecules because steady electric field stretches them out so that they travel end first through the gel matrix in the snake-like fashion. The mode of migration is known as reptation. This DNA can no longer be sieved according to its size. The greater the pore size of the gel, the larger the DNA can be sieved. Thus, agarose gel cast with low concentrations of agarose are capable of resolving extremely large DNA molecules. Pulse field gel electrophoresis is a variation of agarose gel electrophoresis which takes the advantage of the electrophoretic property of the large DNA fragments. Pulse field gel electrophoresis resolves DNA molecules of 100 to 1000 kilobases by intermittently changing the direction of the electric field in a way that causes large DNA fragments to realign more slowly with the new field direction than do smaller molecules. In pulse field gel electrophoresis, pulsed alternating orthogonal electric fields are applied to a gel which forces the molecules to reorient before continuing to move snake-like through the gel. The reorientation takes much more time for larger DNA molecules so that progressively longer DNA molecules moves more and more slowly. Large DNA molecules become trapped in their reptation tubes every time the direction of the electric field is altered and can make no further progress through the gel until they have reoriented themselves along the new axis of the electric field. The larger the DNA molecules, the larger the time required for this alignment. So here in the diagram we can see how the pulse gel electrophoresis work. A very large DNA molecule that are migrating parallel to the electric field in one direction takes more time to reorient in an alternating electric field than do smaller molecules. CHEF pulse field gel systems use a hexagonal gel box that alters the angle of the field relative to the agarose gel. The following are the various pulse field gel electrophoresis: field inversion gel electrophoresis, vertical pulse field gradient gel electrophoresis, contour clamped homogeneous electric field gel electrophoresis, field inversion gel electrophoresis. The field inversion gel electrophoresis apparatus, there is a periodic inversion of single electric field. The field is uniform in both the directions and the forward pulse is slightly longer than the reverse pulse, resulting in movement of the DNA along a straight track. FIGE, that is field inversion gel electrophoresis, resolves DNA fragments up to 2000 kb in length. Vertical pulse gradient gel electrophoresis. The apparatus designed by Gardner uses a vertical gel apparatus with platinum wire electrodes positioned on opposite sides of the gel. The DNA moves first towards onset of the electrodes and then towards the other as the electric field is switched. The net result of these zigzag movements is a straight line from the loading well to the movement of the gel. Because all the lengths in the gel are exposed to the equivalent electric field, there is no horizontal distortion of the DNA bands. Counter-clamped homogeneous electric field gel electrophoresis. In counter-clamped homogeneous gel electrophoresis, electric field is generated from multiple electrodes that are arranged in a square or hexagonal contour around the horizontal gel and are clamped to the predetermined potential. A square contour generates electric fields that are oriented at right angles of 120 degree or 60 degree depending on the placement of the gel and polarity of the electrodes. Thus, it produces a contoured clamp homogeneous electric field by using a combination of low field strengths, low concentration of agarose, low switching intervals, and extended periods of electrophoresis. It is possible to resolve DNA molecules up to 5000 kilobase pairs in length. The limit of resolution of pulse field gel electrophoresis depends on several factors. Pulse strength. This is the most critical factor in all PFGE systems, and the time the electric field is applied in each direction. The longer the pulse time, the more the separation is extended to higher molecular weight DNAs. Temperature. Mobility of DNA molecule increases with the temperature. In PEG or PFG, that is the PFGE, pulse field gel electrophoresis, the temperature is usually maintained at 10 to 15 degree. When higher temperatures are used, separation over a somewhat larger range can be obtained, with the separation window moving to larger molecules at expense of more diffuse bands. Agarose. The agarose concentration is kept at 1% weight by volume. When higher agarose concentration is used, separation occurs over a small range but with sharper bands and decrease of the overall mobility DNA concentration. The mobility of DNA molecules in PFGE is sensitive to the concentration of the DNA, with high concentration leading to lower mobilities. This may affect substantial and results in some sizes that differ by as much as 50 kb. Detection. The standard technique of ethidium bromide is used for staining the gels. For detection the minor species of DNA, the gels are usually destained in water for extended periods of 24 to 48 hours before photography. In molecular biology, pulse field gel electrophoresis has already found widespread applications in the following aspects: determination of size of the genomic DNA, characteristics of the large-scale organization of the telomeric and subtelomeric regions of rice, tomato, and barley, study of higher-order chromatin structure in maize, map-based cloning to isolate genes for which only a variant phenotype and genetic